Next, I'd like to introduce you to our first keynote speaker. He's a world-renowned cryptographer and a professor with the Department of Computer Science at Aarhus University in Denmark. He's widely regarded as one of the world's preeminent experts in the field of secure multi-party computation. He's co-authored multiple foundational papers in the realm of MPC and threshold cryptography, and he's widely known as the co-inventor of the Merkle-Damgård construction, which is widely used in most modern cryptographic hash functions today, including blockchains. He was also part of the core team to develop the first commercial implementation of MPC back in 2008, and has since founded several companies, including CPR and Partisia Blockchain, which we'll hear from later in today's sessions. Please join me in welcoming Professor Ivan Damgård as he provides a highly simplified introduction to the concepts of how key management and security can be dramatically enhanced by using multiple parties where no single party ever has visibility to or possession of a complete key. Ivan, the virtual podium is all yours.
Thanks, Frank, for the introduction, and welcome to my talk. I'm going to be talking about secure computation and how we might use that technology to get better, more secure, more reliable key management. Okay, I'm going to start with a very basic problem research question, if you like, from computer science, named distributed computing. So let's say we have a bunch of machines that are sitting on some network, they're connected, and now the question we're asking ourselves here is, can we make all these machines collaborate so that together they function as if we had just one single machine? However, that one single machine should, seen from the outside, be more secure, more reliable than each of the individual computers would be if they had been on their own. So I mean, that sounds good. Better security is always better, right? But what I mean by more secure here, so more concretely, what it means is that, of course, when we have this network of machines, we should expect that they get attacked. And the idea is that even if some of these machines are taken over by the adversary, so the adversary steals all the data that sits there, takes them over, they do what he says, then even in that case, it should be such that system still works as it's supposed to. Concretely, the adversary can't steal any data from the system, and we still get correct results. So any client that would use this system would get the responses that he expects, even in that case. And why do we care about this? Well, obviously, in this context, it's clear if we can do this, we get a much more secure way to handle crypto assets. If this place is where your digital identity is anchored, and this is where you have your secret signing key for your transactions, then that's the kind of thing that you want, that even under attack, things still work as they're supposed to. However, if any of you had time to think while I was talking here, you might sort of ask a natural question. Can we even do this, right? Because it might seem that if the system stores some critical data, like your secret signing key, for instance, and can use it, I mean, you think that data must be stored somewhere, right? For instance, here, maybe not all the time, but some of the time it might be on that machine. And of course, you have to remember that we don't know in advance which of the machines will be attacked. So if the adversary happens to attack that machine there, then we're in deep trouble. And it doesn't seem like from that point of view that we can even avoid the possibility, at least, of being in trouble. But then, of course, that's the most important probably take-home message from this talk, is that in fact we can solve this problem. So there are solutions here, and the way to think about this is let's do two machines first to keep things simple. And let's say that the secret information we're talking about is a number, which in fact, in the case of secret signing keys, that's really often the case. Let's say it's a number 3. And then what we do is we choose 2 random numbers that just happen to sum to the secret. This could be 5 and minus 2, for instance. And then what we do is we store one number in one machine, the other number in the other machine, so we get a situation like this. And then the point is that if one machine gets attacked, then if you think about it, you can see that the adversary still has no idea what the secret is. Because even if your worst enemy finds out that one of these numbers is 5, then from his point of view, the other number could still be absolutely anything. And 5 plus whatever can make any result. So you really have no idea what S is at the end of the day, or what the number was. That the secret number was 3. So the conclusion here, this is actually a very wonderful insight that we have now, is that even if these machines together know about your secret information, then that data does not have to be located in one single place. And therefore, it also cannot be stolen from one single place. And that's where the added security comes from, actually. So what you've seen here is actually a special case of something more general, something called secret sharing. So the idea here is we have some secret number S. We can share this using something called a threshold T. And the idea is I can make shares, so individual numbers S1 up to Sn, and I can store them in different servers. And then because this was set up using this threshold T, what we can be sure of is that even if the adversary steals T of these shares, he still has no idea what S is. So on the previous slide, that threshold was 1. On the other hand, if I can get hold of at least T plus 1 shares, so if at least T plus 1 of my servers are up and running and willing to help me, I can still get S back, so it's not lost. So one example that's a little bit more general than what you saw on the previous slide is I could, for instance, choose n random numbers that just happen to sum together to my secret S. And this means you need all shares to get S. So in this case, the threshold T is n minus 1. If I have only n minus 1 of these guys, then I'm missing one sum, and that can still be absolutely anything. So I still don't know what the secret actually is. So let's try and see how we can use this thing now, this concept to do more secure signing of transactions. So let's say that this number S is your private signing key, actually. That's used to sign transactions on Bitcoin, Ethereum, what have you. And let's say that simplifies things a little bit. And let's say that the transaction, the message you want to sign is this a number M. And to sign, what you do is that you raise M to power S. That's not what real signature schemes do, really, but it's good enough to illustrate the concept. So therefore, what we do is we have these 5 servers in this case, and I'm going to store one of these little numbers S1 up to S5 in one number in each machine. And now you should imagine that there will be a client, your smartphone, for instance, that sends a request to the system here, please help me to sign M. And then what these servers would do locally is they would take the message and raise that to their own secret number and send this back to the client. So that means now the client has received M to the S1, M to the S2, and so on. So now I'm going to do something absolutely unreasonable. Namely, I'm going to ask you to remember your high school mathematics, nothing less. And the reason is that if you do that, then you will understand that if the client multiplies all the contributions from the servers, so it means you get M to the S1 times M to the S2 times and so on, that becomes the same old M raised to the sum of the exponents. So you get S1 plus S2 and so on sitting up there. And of course, we all know what that sum is. That's just S. So in fact, you get M to the S at the end of the day. So it means that when the client multiplies what he gets from the servers, then you get the signature that you actually wanted. And remark that we managed to do this without revealing S at any point, or even any of the S1 or S2 directly. You can in fact show that a process like this is secure, meaning that if the signature scheme is secure in the first place, which of course we have to assume, then the rest of the process reveals nothing to the adversary that he could use to break the scheme. Even if he watches the entire network transaction that's going on here, this will not help him. Okay, so this is all very nice in theory, the math works out and everything, but you might wonder if this is actually just theory or also relevant in practice, and it very much is in fact, because solutions like this are indeed very practical also for real signature schemes, not just for my example, simplified example here. They're on the market and they're available from many different companies, such as, for instance, the sponsors of this event, it happens to be, so Defense, Fireblocks, Parfin, and Zapier, and many other people as well. It integrates with wallets in the way you expect, so that when you use this, you'll see a perfectly ordinary wallet functionality from the user side. It's just that on behind the scenes, what goes on is that the secret key is being stored and used in this more secure multi-party kind of fashion. You can tune this to all kinds of different signature algorithms that you wish. And you can also choose the setup you want in terms of how many shares, how many servers do you want in total, and how many are required to sign. So in my example before, there were 5 servers, and we required, in fact, all 5 of them to sign. You can also have a smaller threshold if you want to emphasize more the reliability of the system, because that would mean that if some of them crash, the system is still available. And so you can tune this to your liking. I took some example benchmark numbers from the portfolio of Sepia just to give you a feeling for how fast this goes in real life. This is from an actual installation, so it includes all the nitty-gritty practical stuff that you also have to do, including in addition to the mathematics. So it includes database lookup, network access, and so on. There's no cheating here. This is ECDSA, so the Bitcoin signature scheme. 3 smallish machines, 4 cores, nothing fancy. And the setup here is it's secure if at most 1 server is corrupted. And with that setup, you can handle 1,500 signatures per second. You can also scale this up by just throwing more hardware at the problem. If you include, for instance, 6 machines in parallel at each server location, you can handle 11,500 signatures per second. So it's actually pretty decent speeds for a practical application, I would say. So conclusion for this, I would say, is there is indeed some great possibilities here for using secure computation to manage digital assets in many different ways, and you really do get bang for the buck, if you like. You do get more reliability and more security. So with that, I'd like to thank you for the attention and hand the floor back to Frank.